Hi guys, it's me Messi from Messi's Maths, and today I am here to teach you something a bit different. It's definitely differentiation, but it's a bit different as in today instead of going through through lots of rules or or anything like a normal continuation of the syllabus, let's do something a bit different. Let's ask ourselves why we differentiate. Actually no, let's ask ourselves why more on the side of how, actually, not why than why. If you take x squared, most of you might actually know how to differentiate this function. However, what you may not know is how you actually do it, because most of you might just use this. You want to think of the number in the power side going to the left and subtracting it by 1, and that in simplified makes 2x. However, let me actually show you how that might actually work. So let's take it geometrically. Let's make a square with sides of length x that represent, and the area represents the function x squared. Let's make it a bit. Of course, this should be a representation. My drawing skills aren't the best, and we're on a whiteboard. But anyways, sides of length x. Let's say it here. They'll take some time. So now, length. This will the area will represent x squared, and sides of length x. Okay, so this represents a square. This should also be x, so this should also be x, right? Now, if we take the derivative, if you think about dy over dx, you might just think of it as notation sometimes if you're not very well versed. But in reality, there should be a meaning behind dy and dx. And think about it like this: if this is you can add on two pieces. Let's represent an extra addition, representation, of course. I'm trying to remove something a bit tiny, but it's not going to. Anyways, if you add on each side length of dx, okay, then what you end up with is 3 when you can separate it into into 4 portions actually. Now I gotta give some credit to 3 blue, 1 brown. Sorry, 3 brown, 1 blue for me learning this, but I disagreed with him a bit. I should show you the link in the description for that video and his channel, so you guys should subscribe, but be careful because some of his videos are extremely complicated, so watch out. But anyways, if you add on this representation, there'll be a representation. Yeah, a proper representation of dx as an addition on each side. Alright, so if you take this as dx, actually, let's not do that. No, let's do that. And dx. Now this is supposed to represent x. Wait, this here, from here onwards. Around here. Or rather, around on there. X and dx here. Now you'll notice, well, you should eventually notice after I draw it out, that there'll be 3 more pieces. And now, sorry. Sorry about my bad drawing skills. Anyways, for those who know completing the square, this may look similar, and it's good if you know that. Okay? But, of course, one thing you must remember is, this is calculus. even though this for some reason has geometry. Now this is d of dx squared, not d of x squared, dx squared. And this is basically, yes, x times, of course, so that would be x squared plus dx, wait, plus x dx. Okay, and let's do that. Yeah, true, dxx. Sorry for if it looks a bit bad, but x squared plus x dx. And so that would eventually create an equation. Sorry for the time it takes. Okay, so x squared plus two dxx plus dx squared. Now for those who know algebra decently, pretty well actually, you may know that you can factorize it, but for now you don't do that. Okay, so now you can go many ways with this, but let's just go like this. Okay, now first of all, this portion is y, because y is equal to x squared, okay? And we're gonna make a function. So, and this part is dy, and think about it like this. So we take x and add on a tiny, and if we take the derivative, x should be ridiculously tiny. Okay, a really tiny length, even if this representation is large, of x. Okay, we add it on inside on each side of dx. We add a tiny bit, and you also get this because you geometrically, this is what you get. Now, if we were to add that, like here, if we were to add that, basically what we're adding is x on the inside by a tiny amount. And if you know graph transformations, you do x plus dx on the inside, not the outside, because you're adding a dx. Okay, and this will also inevitably, you should also properly change y as well by a factor of dy. Okay, by dy. Okay, so we're adding it on, and this, now what you do is you want dy over dx, right? Okay, and what you do now is you subtract y because we don't need it, and when we subtract from this side, y equals x squared. So what we're basically doing, so what we can take geometrically is remove this side, okay, and subtract x squared. Now subtracting x squared would basically mean removing it, and here as well. So here we get left with this, okay, and now we want, and even if it's a derivative, we can literally use a fraction, dy over dx. So we just divide this entire thing. Let me go to Desmos. Okay, that would be 2 dx root x plus dx squared all over all over dx. Oh, all over dx. And that is equal to 2x plus dx. And now we're going to use something that I unfortunately haven't taught you, but what we're basically doing is removing the, and what will happen in the end is removing dx. Now, since dx, this is not supposed to be any special formula that will help you find with a specific difference. This is supposed to be infinitely small. So when you're finding the derivative of something, you want to find if you want to find the derivative of x squared at 2, 4, you want to find it at that point. So yeah, so what we basically do is use something called limits, and you can basically understand this. You should try and understand this without learning the concept of limits. But you're basically, since dx is supposed to be ridiculously small, we just take it away. Just take it away. Because it's supposed to be at a given point. And the thing about calculus is even if you go ridiculously close, if you take it relatively, now none of you should ever try to be expected to calculate the derivative at a point, okay? This is in relation to x squared. Think about it properly. If you go back and take this, how could you possibly find the derivative of this point? However, you can see a little change in curvature, and if you can see the pattern, see? Now you can find a derivative because there's a function. And even if you go super small, infinitesimally small, you should still find some meaning. Yeah, you should still find a meaning, and that is a gradient. The gradient, the rate of change, even if you go infinitely small, you can still imagine, people can still imagine meaning. Even if you see something that's supposed to not exist in the real world, people can still take meaning. And from this, you should remember. Now, if you take a point like 2, 4, and 3, 9. Okay. You see the dx and the dy, right? And this is to get more and it to be more and more accurate. Yes, to get this to be more and more accurate, what you do is you make it close. Now try like this. Okay, you can find a dy and dx and find the gradient of a line that would directly connect the two, but you are not going to find the gradient of the perfect gradient of this. Now what you need to do is zoom it in perfectly. Let's take 2.001, sorry, 0001, and 000. As you can see, it's ridiculously small. And take the in here. Now the change in y and the change in x are now so much smaller. And in calculus, what you should do is take the difference even more to infinitely small point. And even if limits are a bit ambiguous, what you can do is remove the dx, and that is how you get the d2x without knowing a power formula, a rule. Okay? And that's basically it. Now, let's not leave yes yet. I want you guys, as an exercise, So try find a geometrical representation of the derivative of x cubed, and then try solve it algebraically, and write down in the comments or ask me to post a video about it. Okay, because I'll give you a hint. It involves using a cube rather than a square. And see you everyone. Please remember to like and subscribe. Share this to as many people as possible so that they understand rather than just plugging and chugging. Now, one last thing I should say, or if it is the last thing, one of the last things, if somehow I should just say, sometimes in maths we might just remember formulas, things like the power rule and all kinds of stuff, quadratic formula, how to complete a square, all kinds of procedures and steps. But sometimes you should just stop and think of why we do those. Just stop and think about why we do the things that we might do. Things like completing the square, why does it work? How do you get the turning point? Think about how the quadratic formula even exists. And all these things. Why we use functions, why we use calculus. Sometimes you just stop and think and stray from remembering formulas, plugging and chugging and all kinds of stuff. See you guys.